Welcome to another AQA AS Chemistry video. Today I'm going to be doing a video on the Maxwell-Boltzmann distribution. And yes, okay, so Maxwell-Boltzmann distribution is just a good way of showing you how you can kind of track the number of molecules that have your activation energy, and it's kind of just it's a graph that shows you the activity of molecules and which ones it gives you relevant information to do with the average energy of the molecule, the most likely energy of a molecule, which molecules have the activation energy, and how the graph can change if you change different conditions. And it's just a good way of showing you the activity of molecules once you change different conditions. That's what it's mostly to do. And I'm going to show you the graph, but I'm going to go through where it is kind of like some of the other features of the topic. It's quite easy to grasp once you do it, and it generally 1-mark questions of you in the exam where they ask you to actually draw the graph, and show it, and they may ask you draw the Maxwell-Boltzmann distribution curve if I increase the temperature, right? And I'll kind of go show you what happens, right? So it's very easy to do. Yeah. The Maxwell-Boltzmann distribution of energies is a handy little graph showing you the energy distribution of all molecules in a gas. So the number of molecules is on the y-axis and the kinetic energy of the molecules is on x-axis. Remember, it's kinetic energy because that's the particles are moving. This whole topic is about kinetics, right? So movement of particles, so that's kinetic energy. The origin, so no molecules have zero energy, so the curve passes through the origin at 0, 0. No molecules have zero energy, even if they're at minus 0 Kelvin. The subatomic particles that are within that those compounds, right, or whether it's an atom or an ion or a molecule, the subatomic particles still have energy to move around. So it's described that no molecule has zero energy. So the only time you'd get zero energy is when there's zero molecules, hence 0, 0. The peak, so there's a peak in the middle, and this represents the most likely energy of any molecule. There are more molecules with this energy than any other energy. So don't get confused with the average energy. The average energy is just, I'll show you when I get to the graph, is just to the right of the peak. So just right of the peak is the average energy, but the tip of the peak is just representing the most likely energy that all the particles are most likely to have, or they have. It's just the energy that the majority of the molecules have, if that makes sense. So the majority of molecules have this energy, but it's not the same as the average energy. The average energy is obviously just taking the average of all the molecules all together, and it's usually just right at the peak. But yeah, I'll go through that soon. So the area underneath the graph. So the area underneath the graph gives the total number of molecules. So kind of like in maths, if you did A-level maths, you know that the area underneath the graph is if you integrate it, if you wanted to work out the area underneath the graph, you have to integrate. I think so. I haven't done maths in a long time, but you have to integrate the graph. But listen, don't have to worry about that. Don't get confused by the x-axis. Don't get confused by the x-axis either, because that just represents the, I should have said y-axis. Yeah, sorry, my bad. That's my bad. Don't get confused by the y-axis. That just represents the number of molecules with the energy. So when I should probably go through the graph to actually show you what I mean. But there'll be on the y-axis is your number of molecules, and on the x-axis is your energy. So don't get confused when you see the y-axis and see the number of molecules is where the peak is. No, that's not it. The area underneath the graph represents the total number of molecules. The y-axis is just showing you the number of molecules that have that energy. So yeah, you don't have to worry about this like in maths where you have to integrate the graph. For A-levels, all you need to know, you just need to know that the area underneath the graph represents the total number of molecules. You don't have to integrate anything like that. There's no integration or differentiation in chemistry. I know there is in physics, but in chemistry you don't have to worry about that, so that's fine. So molecular energy. So the average energy is just to the right of the maximum peak. The tail of the graph is asymptotic. to the x-axis, and this just means that it tends to 0, like a tan curve, right? It just tends to the line, or tends to, or I could say 1 over x. No, is it 1 over x? 1 over x, or yeah, like a 1 over x curve, where it just kind of asymptotically tends to the x curve, but it never touches the x-axis. And this represents that there's a small possibility of having a very high energy molecule, which is still possible, right? So this is what I mean, right? So let's go through. I should have went through this part first, but or gas, the origin 0, 0. As I said before, that's not really, I don't think that makes sense. The area underneath the graph. So the area underneath all of this graph, that represents the total number of molecules. So this area that's represented underneath the graph is the total number of molecules in the sample, right? The number of molecules here. This is just the number of molecules that have that particular energy. So it doesn't. If you go to here, if like, don't get confused saying that this is the total number of molecules. No, that's just the number of molecules that have this particular energy. And in this case here, this peak is the most likely energy of molecules. This maximum peak is the most likely energy of molecules, and just right of the peak is the average energy of the molecules. This line here represents the activation energy. So the activation energies. So we can mark the activation energies in the Maxwell-Boltzmann distribution, and this allows us to view the number of molecules with the energy to react. So this here represents the activation energy, right? And so energies that have, think about it right here. So if the energy is more than its activation energy, that means that those particles have the activation energy to react. And if the energy is less, or should be on the left, it means these particles don't have they don't have this activation energy. They haven't reached the activation energy in order to react. So on the left hand side of the activation energy mark, molecules have less energy than the activation energy, and so they can't react because they haven't reached the activation energy yet. And on the right side, molecules have more energy than the activation energy, and so they can react. So the molecules that are on this side of the curve have already breached or exceeded the activation energy, and they will have the activation energy, or they will have energy greater than the activation energy, which means that they have energy in order to successfully collide and react. Whereas on the left side, they don't have the activation energy, so they don't have enough energy to successfully collide and react. And that's the main point, right? That's what you would say in your exam if they ask you, well, as they say, they either have the activation energy to successfully collide and react, or they have or they don't have the successful energy to collide and react. And that's just between the two. Don't have the successful energy to collide and react, or have the successful energy to collide and react. And that's the point that gets you the marks. So activation energy. The Maxwell-Boltzmann graph can show us where the activation energy lies with respect to that energy distribution of the molecule. So the mark. So we can mark onto the distribution a line showing where the activation energy lies. The line is vertical. This is because the x-axis represents energy, and so a vertical line will mark a specific energy. So on the left hand side of the mark, the molecules have energy below the activation energy. On the right hand side of the mark, molecules will have energy greater than the activation energy, and I think we've already gone through that plenty enough now. So the effects of heat on the Maxwell. So now I'm going to go through the different effects of different conditions on the Maxwell-Boltzmann distribution curve. So the important thing to remember here is that the area underneath the graph is the number of molecules. So heating can't increase the area of the graph, and that's just coming back to, you know, the law of conservation of mass. No molecules or atoms can be created or destroyed. So if you just heat a compound, you're not gaining more molecules, but because only adding new molecules can do that. But heating does increase the average energy of the molecule. So we can see that heating the reaction moves the maximum to the right, but also lowers the number of particles with that energy. So here's the graph, right? So think about it carefully, right? So if the peak is the most likely energy of the compound, moving it to the right shows that because see, this graph right here represents 200 Kelvin, this here represents 300 Kelvin. The peak is moved to the right, which makes sense because if we're increasing the temperature, that means that more particles, the most likely energy the particles will have will be increasing, right? It would increase because if it's a higher temperature, they have more kinetic energy to move around. And if you see here, the number of molecules there's less molecules with that have the peak is more broad now. Because remember, it has to, if you're making it more wider, remember the number of molecules has to stay the same. The area underneath this graph and the area underneath this graph is exactly the same. So if you're gonna make a graph that's going from this, and it can't be the same height, right? It needs to, if they both have the same area and one's kind of larger now, it's gonna become a bit smaller, right? To accommodate the fact, to show the fact that the area underneath the both graphs is exactly the same. Alright, so now this is also a very big part here, right? Because the temperature is increased, not only have you got the graph shifting to the right, the entire graph shifts to the right? So then that means that more particles also have the activation energy, which makes sense. When you increase the temperature, more particles have the kinetic energy that's more than the activation energy to successfully collide and react. And that's just being proven here, that there's more particles with the activation energy to successfully, there's more particles that have either the activation energy or kinetic energy that's greater than the activation energy to successfully collide and react. And those are the most important points here. Graph shifts to the right, lower, and more particles have the activation energy. So molecule speed. So think of a marathon, right? Because I think they might get confused by when people say the words like, whenever you think of a reaction, everyone thinks that if you increase the temperature, all the molecules will have the same energy. No, it's not like with mass spectrometry where all the particles have the same kinetic energy. No. If you increase the compounds, right, over time, more of them will be close enough in kinetic energy. But much like people in a marathon, not all the molecules will move at the same speed. If you look at a marathon, some people will move faster than others, and that's kind of what it is. Generally, there'll be a large body of people that maintain the same speed, but there'll be some people who are generally slower, some people who are generally faster, and that's what's happening. That's what it is here. The majority is here. That's the majority, the most likely energy. Some of the people will be a bit slower, some people a little bit faster, and that's what's represented here, is that not all molecules move at the same speed. Some molecules are faster than the average, some are slower than the average, but most of them are around the average. The next one is about catalysts, right? The effect of a catalyst on Maxwell-Boltzmann distribution. There's many, but I'm only going to go through these two, and in the next video I'm going to be going into a bit more depth on other things like concentration. Right, but this is the effect of a catalyst on Maxwell-Boltzmann distribution. So as before, when talking about the effects of heating on the Maxwell-Boltzmann distribution, the number of molecules is represented by the area underneath the graph, and so nothing can increase the area underneath the graph unless we add more reactants, or i.e. we change the concentration. So this is just following the law of the mass of conservation law, or law of conservation of mass, I should say. So applying a catalyst doesn't increase the energy of the compounds, because remember, we have to remember what the definition of a catalyst is. A catalyst is, that's the definition there, a substance that would increase the rate of reaction whilst not getting used up in the reaction. It does so by allowing the reaction to occur under a new reaction pathway that has a lower activation energy. And that's literally what the graph shows here. So I want you to think, so if this is a Maxwell-Boltzmann distribution curve, right? So given that you know the definition of what catalyst is, and you kind of understand what the different parts that I've already shown you what different parts of the graph represent, I want you to try and pause the video now, and I want you to try and mark where the activation energy is. So this is the activation energy when no catalyst is present. I want you to draw where you think the activation energy is, or at least kind of have an idea of where the activation energy is when the catalyst is present. So pause the video now and try to answer that. Alright, so where would it be? So a catalyst would increase the rate of reaction by allowing, without getting used up in the reaction, by allowing the reaction to take a new pathway with a lowered activation energy. So that means if the activation energy is lowered, If energy is going this way, right? So that means that we have a lower value, a lower x value. So the activation energy is actually going to be more like here. Obviously, do it with ruler. But what does this mean, right? It makes sense, because I think if some people may have accidentally wrote it here, it wouldn't make sense here, because then if I drew it here, right, that wouldn't make sense. That means that if I increase the temperature, it means that the activation energy would increase. It means that it's harder for the reaction to happen, or more energy is needed for the reaction to happen when I increase temperature. And it also means that less particles will have the activation energy for the reaction if I increase the temperature. So that's why I've drawn this here in line with the definition. By moving it over to the left, it means that the reaction is still occurring, as I haven't changed any of the temperature or the pressure or anything like that, but the reaction is occurring as it does, but under a lower activation energy. So that means that more of the particles have the activation energy, or have energy greater than the activation energy, greater than or equal to the activation energy, I should say. So more particles have energy that's greater than or equal to the activation energy to successfully collide and react. And that's what's happening with the catalyst. And that's what's represented here. So when you have a catalyst, all that happens is that the activation energy shifts to the left a bit. I may have been a little bit over dramatic here by moving it by this much, but the idea is that you understand what's going on. It's moving to the left. And yeah, that's it. So hopefully this video was helpful.